This is Decoded, the video engineering podcast by Fora Soft. Episode 2, Sampling and Where Aliasing Comes From.
So right now, you are probably looking at a screen,
Most likely, yeah.
right? And whether it's your phone or a laptop or even just some massive TV on your wall, it feels like this perfect continuous window into reality.
Just a seamless stream of light.
Exactly. But it's actually a hallucination.
A total illusion.
Yeah. You are staring at this rigid, totally inflexible grid of millions of deliberate data gaps, and they're all designed to just mathematically trick your brain.
It is wild when you really think about it.
It really is. So welcome to this custom deep dive. Today we are exploring the invisible magic and honestly the intense mathematics that happens in that tiny split second between a camera lens capturing the real world and a video file actually playing on your device.
And we're drawing from a really brilliant source text today, a chapter specifically on spatial and temporal sampling.
Right. We're going to peel back the layers on how the actual continuous physical world is chopped up, measured, and heavily manipulated to fit into these digital boxes.
Because it's not a direct copy, it's heavily filtered.
Exactly. So, okay, let's unpack this, because before we can even talk about the weird visual glitches you see all the time, we have to look at the baseline engineering problem.
Right, which is just how do you turn fluid reality into cold, hard numbers?
Exactly.
Well, the foundational concept pulling all this together is sampling.
Right.
And, you probably already know that digital media is made of pixels and frame rates, but let's look at what that actually means for the physics of light.
Because the real world doesn't operate in frames.
No, not at all. Motion flows without breaks. Light gradients transition infinitely. But a digital camera sensor, it cannot record an infinite stream of information.
It'd be impossible.
Right. It has to measure a continuous signal at regular, discrete intervals.
Yeah, and the source text actually gives this really great thermometer analogy, which I think sets a good baseline.
Oh, yeah, the river analogy.
Yeah, so imagine you're tracking a river's temperature. You dip a thermometer in the water, once every minute, and you record the number.
So your data log is just one snapshot per minute.
Right. But if a sudden, 10-second surge of boiling hot water rushes past between minute 3 and minute 4...
You totally miss it.
You completely miss it. Your measurements landed just before and just after the event.
And that, right there, introduces the central tension of all digital recording.
Which is?
The more frequent your measurements, your samples, and the less reality you miss. But frequent sampling creates these massive, unmanageable piles of data.
Right, and we want small, compact files for streaming and storage.
Exactly. But reducing the sample rate introduces catastrophic risk. And video multiplies this risk exponentially because it isn't just a thermometer checking one thing.
Right, video has layers.
Yeah, video is sampled on 3 independent axes simultaneously.
Okay, so you're sampling spatially in 2 directions, right? Horizontally across the columns of pixels and vertically down the rows of pixels.
Yep, that's your X and Y.
And then you are sampling temporally through time with your frames per second.
The Z-axis, or time axis.
Right, so 3 separate axes of measurement, which basically means 3 independent vectors for the math to just completely fall apart.
Exactly.
Right. Wait, let's talk about the math falling apart, because that leads to the golden rule of sampling that the text really focuses on.
The Nyquist-Shannon theorem.
Yes.
So this was theorized in the 1920s and mathematically proven later by Claude Shannon. And it basically dictates that to capture a continuous signal accurately, you must measure it strictly more than twice as fast as the highest frequency present in that signal.
More than twice as fast.
Right. The absolute maximum frequency a digital system can handle is exactly half of its sampling rate. And that threshold is what we call the Nyquist limit.
Okay, so if you are trying to record, say, a hummingbird's wing beating 100 times a second, you must sample at a rate of at least 201 times a second.
Exactly. You need that absolute minimum to capture the full cycle.
But what is so counterintuitive to me is what happens when you fail.
Oh, when you undersample.
Yeah. If you measure too slowly, the fast information you miss doesn't just render as a blank spot or a gray blur. It actively disguises itself.
Yeah, it creates a phenomenon known as aliasing.
Aliasing.
Right. When high-frequency details slip through the gaps in your sampling grid, they don't just vanish. The mathematics of the sampler process actually forcefully fold those high frequencies down into lower frequencies.
Which is wild.
It is. The system outputs a completely false but entirely realistic-looking new wave pattern.
It's like, okay, think about blinking rapidly while watching someone run across a room.
Okay.
Your brain tries to stitch those fragmented visual glimpses together, but because of the data gaps, the moments your eyes were closed, your brain might totally misinterpret the sequence of their footsteps.
Right.
And you might hallucinate that they are, like, moonwalking backward. The missing data literally creates a fake reality.
That is a perfect way to visualize it. Undersampled details fold into structural lies.
Structural lies. I love that phrasing.
Yeah, and this is exactly why video engineers consider aliasing their absolute worst enemy.
Because it's deceptive.
Totally. I mean, a soft, blurry image is immediately recognizable as a flaw, right? You see a blur, you know it's bad.
Yeah, obviously.
But an aliased image is dangerous because it looks incredibly sharp. It feels detailed. Yet the detail you were looking at literally did not exist in the physical world.
Okay, so we know the theory. If we break the Nyquist limit, the math essentially hallucinates. But how does this actually manifest for you, the listener, watching a screen in everyday life?
Right. What does it look like?
Exactly. And it turns out aliasing wears 3 distinct masks, one for each axis of video. So let's look at spatial aliasing on patterns first.
The wavy shirts.
Yes. Have you ever seen someone on the news wearing a finely striped shirt, and the shirt suddenly starts swimming with these bizarre, wavy, colorful bands of light?
Yeah. What's fascinating here is the physical interaction happening right on the camera sensor to create those bands.
Break that down for us.
So those wavy patterns are called moiré. The fine stripes on the shirt represent a high-frequency spatial pattern, rapid alternations of light and dark.
Right.
And the camera sensor is a rigid microscopic grid of photosites. So when the physical frequency of the shirt's stripes is tighter than the Nyquist limit of the sensor's pixel grid.
The camera just can't resolve the line.
Exactly. The interference between the physical pattern and the digital grid creates this sort of beat frequency, and that renders those wide, swirling, psychedelic patterns you see. Moiré is basically the visual artifact of a spatial math violation.
That's crazy. And the second phase of aliasing is also spatial, but you don't even need a complex pattern to trigger it.
No, you just need a single slanted line.
Right. We call them jaggies.
Yeah.
Because a real-world edge, say, like the roofline of a building against the sky, is perfectly smooth.
Naturally, yeah.
But when the camera forces that shallow continuous slope onto a rigid square pixel grid, and that slope's frequency exceeds the grid's resolving power, it snaps into a harsh staircase pattern.
Which is super common in like old video games or low-res video. Yeah. And that leads naturally to the third phase, which happens on the time axis. Temporal aliasing on fast motion.
Oh, this is my favorite one.
It is most famously recognized as the wagon-wheel effect.
I just love the math behind this one. You see it in classic westerns all the time. A stagecoach is racing forward, dirt is flying, but its wooden wheels appear to be slowly, steadily spinning backward.
It totally breaks your brain the first time you notice it.
It does. And the source text actually breaks down the exact arithmetic of why this happens. So, a classic film shoots at 24 frames per second.
Right.
Following the Nyquist theorem, half of that frame rate is our absolute limit, so 12 cycles per second. But imagine the stagecoach wheel is spinning fast enough to make 18 full revolutions per second.
Well, 18 cycles per second violently exceeds the 12-cycle Nyquist limit of the film camera.
So let's look at what happens in that literal blind spot between one frame and the next. In that tiny 124th of a second gap, the wheel physically rotates 3/4 of the way around. So a wooden spoke that was pointing straight up at 12 o'clock moves all the way around to 9 o'clock. But your brain, viewing the playback, acts like an incredibly lazy computer.
It always seeks the shortest possible path between two data points.
Yes. It absolutely refuses to perceive 3/4 of a rotation forward. It just sees the spoke move from 12 o'clock to 9 o'clock and assumes, oh, it must have shifted 1/4 of a turn backward.
The rapid forward motion folds neatly into a slow reverse motion. It is just a mathematically perfect temporal hallucination.
It's so cool.
And the exact same mechanism makes helicopter rotor blades look completely stationary on a 30 frame per second digital camera.
Oh, I've seen those videos.
Yeah. If the blade happens to rotate exactly once per frame, it just looks like it's floating in midair.
Okay, but this brings up a glaring contradiction.
What's that?
Well, if breaking this fundamental rule guarantees our screens will be filled with psychedelic shirts and jagged edges and physics-defying wheels, why isn't the internet just a massive, glitchy mess?
That's a very good question.
Like, why does most of the video you watch actually look pretty good?
Because the industry learned how to aggressively manage the sampling. But to understand the fixes, we first need to look at how engineers actively exploit our biological weaknesses to break the Nyquist limit on purpose.
Here's where it gets really interesting.
Oh, yeah.
Because aliasing is constantly framed as the ultimate enemy of the image. But the source text reveals that to save data, engineers are intentionally undersampling video all the time.
Constantly.
And you rarely, if ever, notice it.
Because it hinges on how video codec, the software that compresses and decompresses video, how they actually process information.
Right.
A raw video file does not actually store a red, a green, and a blue brightness value for every single pixel. That would be massive.
The file sizes would be astronomical.
Exactly.
Yeah.
Instead, codecs transform the image into two distinct components. You have luma, which is pure black and white brightness, and chroma, which contains all the color information.
And they do this purely because of the anatomy of the human eye, right?
Yep. Yes, our biology.
Because our retinas are packed with rods, which detect light and dark, and cones, which detect color, and we have vastly more rods than cones.
Yep.
So we are incredibly sensitive to shifts and contrast. Like, you will notice a blurry shadow immediately. But our biological ability to resolve fine, sharp color detail is actually pretty terrible.
Engineers realized decades ago that preserving high-frequency color detail is a total waste of data because your eye physically cannot even see it.
Right.
So they created chroma subsampling, which is essentially a method of intentionally throwing away color pixels just to thin out the file.
And the text outlines the three main formats for this. So there's 4.4.4, which is pristine.
Full color resolution for every pixel.
You're right. No rules broken.
Yeah.
Then there is 4.2.2, which basically discards half the color data horizontally.
Still pretty good quality, used in a lot of professional cameras.
Sure. But the heavy hitter, the format underlying basically every YouTube video, Netflix stream, or FaceTime call you've ever used is 4.2.0.
The standard for delivery.
Yeah. 4.2.2 halves the color resolution horizontally and then halves it again vertically.
Right.
By doing that, it strips away roughly 50% of the file's total data footprint before the codec even attempts to compress anything.
It's remarkably efficient, but, the nomenclature of those numbers, 4.4.4, 4.2.2, 4.2.0, it causes endless confusion.
Oh, totally.
Because you might logically assume the 4 represents 100% of a signal, or the 0 means the blue channel is entirely missing.
Yeah.
But neither is true.
No. They are essentially just these archaeological artifacts from a 1982 broadcast standard known as BT.601.
Yeah.
The number 4 actually represents a specific analog frequency, 4 times 3.375 megahertz, resulting in 13.5 megahertz.
And the reason 13.5 megahertz was chosen as the baseline for global digital video is purely political and arithmetic.
This part blew my mind.
It's so weird, right? During the Cold War, the U.S. and Japan used a 525-line television system, while Europe used a 625-line system. 13.5 megahertz was basically the elusive mathematical holy grail that divided perfectly into both formats, allowing for a unified global digital standard.
So the arbitrary math just stuck, and we still use those labels today.
Yeah.
And the 0 in 4.2.0 is equally misunderstood. It describes a geometric line pattern on the screen. So in a 4.2.0 video, the pixel rows literally alternate their behavior.
Right.
The first line of pixels contains half of its normal color samples, but the second line of pixels contains 0 color samples of its own. It borrows its color entirely from the lines above and below it.
And it isn't just the final video file pulling this trick, by the way. The camera sensors themselves are faking it before the video is even recorded.
Yes, the Bayer filter.
Right. The source details the Bayer filter, which is this microscopic physical mosaic placed directly over the camera sensor.
Okay.
So 50% of the pixels on the sensor are filtered to capture only green light, 25% capture red, and 25% capture blue.
Wait, they stack the deck with green.
Yeah, because the human eye derives the majority of its perceived sharpness specifically from the green spectrum.
Okay, so that means a single photosite on a camera sensor only ever measures 1/3 of the light spectrum at a time.
Exactly. The camera's image processor has to perform a heavy mathematical operation called demosaicing.
Right.
To figure out how much red should be in a green pixel, the processor literally analyzes the neighboring red pixels and extrapolates the difference.
Wait, I need to pause here because this is just absurd.
It really is.
Between the Bayer filter on the actual camera lens and the 4.2.0 chroma subsampling in the streaming codec, true, pixel-perfect color video basically doesn't exist for consumers.
Essentially, no.
Like, Half of the color I am looking at on my screen right now is essentially a mathematical hallucination generated by the computer guessing based on surrounding pixels.
It is entirely interpolated, yes.
Yeah.
Your device is painting by numbers, but it's using an incomplete set of numbers.
That is wild.
And while human biology masks this deception beautifully most of the time, the text points out exactly where this mathematical house of cards collapses.
Which is?
Presentation graphics.
Ah, right. Red text on a white background.
Exactly. If you're watching a screen recording with crisp, highly saturated red text against pure white, you are looking at a massive high-frequency color jump.
Right, a really sharp transition.
Because 4.2.0 subsampling smears color blocks across multiple lumapixels, that sharp red edge will just bleed. You will see this blocky, blurry color fringe bleeding out into the white space.
Yeah, it looks awful.
The missing color data is suddenly painfully visible. And that is exactly why professionals working with digital graphics or video game captures must switch back to those bloated 4.4.4 full-resolution profiles.
Okay, so we can aggressively cheat the system with color because our human eyes are biologically weak, but that doesn't solve the structural geometry problems.
Right, the moiré and the jaggies.
Yeah. We still have to fix the spatial moiré on striped shirts and the temporal wagon wheels. If we have limited data and fixed sensor grids, how do engineers actually prevent spatial and temporal aliasing from ruining the image?
By adhering to the golden rule of anti-aliasing.
Which is?
Smooth first, thin second.
Smooth first, thin second. Meaning you have to deliberately destroy the high frequencies in the physical world by blurring the image before the sampler even has a chance to measure it.
This is the critical mechanism. If you let a high-frequency detail hit the sampler, the aliasing artifact is instantly baked into the data mathematically.
It's permanently encoded.
Exactly.
Yeah.
No amount of post-production processing can undo it. The false pattern becomes a permanent part of the signal. So the hardware and software industries built 3 lines of defense to guarantee that the smoothing happens upstream.
Okay, let's go through them. The first layer is deeply physical. It happens right at the sensor. It's called an optical low-pass filter, or OLPF.
Yes.
It's literally an actual piece of birefringent crystal permanently mounted directly over the camera sensor.
And birefringence is just a fascinating property where a material has 2 different indices of refraction depending on the polarization of light.
Right. So when a beam of light hits this crystal, the crystal physically splits the single ray into 2 slightly offset rays.
Yep.
Then a second layer of crystal splits those 2 rays again, resulting in 4 rays.
So it takes a single microscopic point of light and spreads it perfectly across 4 pixels.
It induces this microscopic, incredibly calculated blur. It softens the ultrafine physical details just enough to push them below the sensor's Nyquist limit.
And that completely eliminates moiré while maintaining the illusion of overall sharpness.
It's brilliant. So that physical crystal handles the spatial X and Y axes, but layer 2 handles the temporal axis time.
Right. And this is accomplished using a 180-degree shutter.
Okay, how does that work?
Well, rather than snapping instantaneous frozen snapshots, the camera's shutter remains open for exactly half the duration of a single frame.
So if you are shooting at 24 frames per second, the shutter stays open for 148th of a second. This intentional exposure time allows fast-moving objects to literally smear across the physical frame. We just call it motion blur, but mathematically it acts as a temporal low-pass filter.
Right, the blur actively destroys the high-frequency temporal data.
Okay, but consider the inverse scenario. If a director decides to shoot an action sequence with a hyper-fast shutter speed, say 18,000th of a second.
Like in those intense war movies.
Yes. Every single frame is captured razor sharp. There's 0 motion blur. But by removing the blur, they allow frequencies well above the Nyquist limit to hit the sensor.
And the resulting footage suffers massive temporal aliasing.
Fast motion looks incredibly jarring, choppy, and strobing because the brain can't stitch those razor-sharp gaps together.
Which brings us to layer 3, which is entirely software-based.
Okay.
Let's say you shoot a pristine 4K video, but you need to upload it to a platform that downscales it to 1080p.
Pretty common scenario.
Yeah. But by having the physical dimensions of the video, you are having your digital sampling grid, which immediately lowers your Nyquist limit. If you just throw away the extra pixels, you'll induce massive aliasing. You have to blur the digital image before discarding the data.
Right, and the source text highlights FFmpeg scalars to explain the mechanics of this software blur.
Yeah, when resizing an image, algorithms use taps, to determine the color of the new pixels.
And a tap basically refers to how many neighboring pixels the algorithm analyzes, right?
Exactly.
So if you use the cheapest method, the newest neighbor scaler, it uses one tap. It literally just looks at the closest pixel, copies it, and deletes the rest.
It applies zero filtering and creates hideous jaggies.
Yeah, it's terrible. The bilinear scaler uses two taps, which creates a very primitive, weak blur. But the gold standard for video is the Lanczos scaler.
Lanczos uses 6 taps, meaning it looks at a wide radius of surrounding pixels to calculate the new value. But more importantly, it applies a complex mathematical weight to those pixels using a truncated sync function.
Which honestly sounds terrifyingly complex.
It does.
But essentially, a sync function is just a wave that ripples outward. It gives positive weight to close pixels and negative weight to further pixels.
It acts as an absolute brick wall filter.
Right. It perfectly chops off the high frequencies while preserving the sharpest possible edge right below the new Nyquist limit.
Yes.
So what does this all mean?
It means that every glitch, every moiré pattern, and every jaggy you see on a screen is a fundamental failure to properly filter reality before attempting to measure it.
You know, there is this incredibly relatable pitfall in the text about a wedding videographer.
Oh, the lace dress example.
Yes. So they shoot a gorgeous wedding, they deliver a massive 4K file to the client, but the bride's intricate lace dress is swimming in neon wavy moiré patterns in every wide shot.
A nightmare for the editor.
Total nightmare. The videographer panics and blames the compression codec or tries to re-export the file at a massive bitrate to, like, fix the quality.
Which won't work at all.
No. It's like trying to unbake a cake. You cannot fix a baked-in structural flaw by just throwing more high-quality frosting, more bitrate on top of it.
Yep.
The videographer used a camera that lacked a strong physical OLPF crystal, the frequency of the lace physically exceeded the sensor's limit, and the matte hallucinated. The glitch was codified the exact millisecond the light hit the sensor.
If we connect this to the bigger picture, it really establishes an absolute law of digital media.
Which is?
Aliasing is always a sampling violation upstream. To fix it, you cannot rely on post-production. You have to go back to the source of the measurement.
Wow. We have journeyed through some dense engineering today.
We really have.
I mean, we went from dipping a thermometer in a river to mapping the exact frame-by-frame math of why wagon wheels spin backwards.
Yeah.
We uncovered that the color on basically every screen we look at is half-faked through 4.2.0 subsampling, relying on our biological blind spots just to save data.
Painting by numbers.
Exactly, and we dissected how engineers use light-splitting crystals, motion blur, and sync function algorithms to protect us from a glitchy, aliased reality.
And yet, there's one final fascinating nugget from the source material that hasn't been discussed yet.
Oh.
Yeah, and it beautifully ties this entire philosophy together. We spent the whole time talking about how the physical geometry of video is heavily manipulated to fit perfectly into mathematical grids.
Right.
Well, the exact same rigid logic applies to the audio you are listening to right now.
Oh, the audio sample rate math? This is wild.
Consider music.
Yeah.
The global standard sample rate for a CD or a digital music track is 44.1 kilohertz.
Okay.
But if you look at the specs for professional digital video, the audio sample rate is universally forced up to 48 kilohertz.
And it isn't because 48 kilohertz provides this vastly superior high-fidelity listening experience for the human ear, right?
No, not at all. It is purely about structural arithmetic. 48,000 divides perfectly evenly into all the standard cinematic and television frame rates.
So 24, 25, and 30 frames per second.
Exactly. At 24 frames per second, 48,000 yields exactly 2,000 audio samples per frame.
Which means a video editor can place a razor blade tool on any exact frame boundary in their timeline, make a cut, and they will always cleanly slice between audio samples.
Right.
They will never be forced to mathematically split a single microscopic audio sample in half, which would basically corrupt the digital file.
Exactly. It creates a unified, unbreakable grid. The single agonizing exception to this rule is the old NTSC broadcast standard of 29.97 frames per second.
Oh, man.
Because 29.97 is a fractional number, it refuses to divide cleanly into 48,000.
So what happens?
Well, to keep the math from falling apart, audio software is literally forced to run this messy, repeating cycle across 5 frames, bundling exactly 8,008 audio samples just to sync back up with the video grid.
Just to make the numbers work.
Just for the math.
Which leaves you with a pretty wild concept to chew on after this deep dive. The next time you are staring at a screen, immersed in a beautifully shot film or a crisp YouTube video, just remember, You are not looking through a perfect organic window into the real world.
Not even close.
No, you are looking at a heavily filtered, intentionally blurred, heavily subsampled, meticulously engineered set of measurement.
Yeah.
And it really forces you to wonder how much of the pristine, seamless digital media you consume every single day is actually shaped entirely by the desperate need for perfect, invisible mathematical convenience.
That was Decoded, the video engineering podcast by Fora Soft. Thanks for listening, and see you in the next episode.